All right, so let's get started. So as you correctly analyzed and discussed, you can solve for this value of, or this process just by having that value of gain using your Ruth-Hurwitz approach. And as we talked about a little bit in lab, what the lab instructor did was perhaps a little bit more detailed than what we're trying to do. Again, why not use the simplest, easiest tool? And it's not a put down of his tool, but let's just do something simple and straightforward that gets the job done. I guess the concept is, why not use a hammer instead of using a sledgehammer to really work hard and to be able to pound a nail into it? So that's the analogy that I think of. The other thing too is on the FE, you would be doing a Ruth-Hurwitz. There are some calculations that you'd use a Ruth-Hurwitz. With the method that he did, I'm not exactly sure. All right, so the last question is plot the curve of K that divides the regions of stability and instability and indicate the plot, which is the stable region. So that immediately should tell you have to do a pole zero map, correct? Because when we talk about stability, it's either in the left-hand half plane or in the right-hand half plane. So that's the only one that you'd indicate that. So the next question is, does anybody have their lab that they can give me the transfer function? Okay, let me bring up MATLAB. And again, all this stuff was running, as I mentioned before class, I had some computer issues, and so I had to reboot my machine. So it's going to take me a few minutes to get up to speed. So I apologize for being slow, but sometimes you can't beat technology.
Would it be multiple? Are you applying multiple zero maps?
Say it again?
Are you applying multiple zero maps to one of these A or?
Yes, I will end up doing multiple ones. Yeah. Oop, wrong button.
Yeah,
R locus. You could certainly do that, but all you need to do is this root locus plot. So we're plotting the roots, right, of our characteristic equation. And we're allowing some value of K to vary. K is a real number. It's not a complex number. It's a real number. So when you do your transfer function, so what was your transfer function?
A over.
And I'm just going to put a 1.
That's U+A.
Hold on. S cubed. Yeah.
That's A squared.
Yeah.
Then U, then K.
So that's my transfer function. So now if I do my root locus, actually, I want the root locus plot. It does it here as well with just root locus. The computer seems to be extraordinarily slow this morning. It does it, okay. So here is a plot of the roots. So it's hard to see, and again, we're jumping ahead a tiny bit, but that's okay. You know, today's the day before break, so we can take our time a little bit. We don't have to go crazy. But remember what we do, and I've been saying this in a little bit last semester when I said, how many poles do you have in a system? Let's say you have 3. Then how many zeros are you going to have? 3? What if I only have S plus 1 in the numerator? Yeah, very good. If you include the fact that you have 2 zeros at S equals infinity, remember we do our limit function, you always have the same number of poles as the same number of zeros. I wasn't saying you were wrong. I was just trying to get people to think. So in a root locus, if your value of K, so K is variable, if you're allowed to increase the value of K, that's going to change the roots. And as you increase K larger and larger and larger, approaching infinity, your roots are going to start at the real roots, whatever those are in your base equation, and then they're going to end at your zeros. So you do a root locus, you start at a pole and you end at a zero. So you can see here, I'm starting and starting. So these are X's, those are poles. Over here, there's an X, and you can see I stay on this real axis. That's because there's a pole, a zero way out at S equals infinity. What about over here? There are also a bunch of poles way out over here at S equals infinity. So when you do a root locus plot, you're actually plotting all the possible poles as you allow K to vary. And go ahead.
How does it know what value K is?
It just allows it to be whatever value it wants to be. So all these, this is going to start, if I look over here and I hover. Oops, I'm getting, so I'm going to go in a little bit more. There we go. So you can see, oh, it's really slow today. So you can see what the gain is. Gain is 3.42. That's the value of K. So when you pick a value of K of 3.42, you get a pole at minus 0.361. Okay. Now, as I increase K, look at what happens to my gain over here. 7.1. And then when I get over here, I'm increasing my K, 17.1. It's the same thing over here. I started at my value of gain, 21.6. I go out over here, 1,150. So this is just a way of plotting the roots as K equals 0. It's called root locus. So if people had thought about it a little bit, you actually would have said, plot the curve of K that divides the region of stability and instability and indicate on the plot which is the stable range. So really, you can't really plot a curve K. You're really plotting the roots as K is increased. All right.
Is K always going to be like the form of K over?
Usually you have usually you have a feed forward gain, which is just a constant. And you can do that way. Yep.
And then in between the empty space between those two poles, between that there's not.
Yeah, so if you want an outcome that you have something that lives over here, somewhere between -5 and let's say -4, you can't get there from here. That system will never give you a pole. That's why it's blank over here.
So depending on the gain, you can have poles
Anywhere you want, yeah.
But then why would you have different colors?
The reason why you have different colors is it just shows you this is one root loci. That's the singular. So this is one root loci and it shows that direction. There's another root loci that starts here, heads to the point, and then goes in this direction. So that shows you as the value of K increases, that root loci goes in this direction. It really doesn't matter for all intents and purposes. It only indicates for us just which way it goes. The other interesting thing too, which is, remember what we said a long time ago about complex roots? They have to be complex conjugates, right? Does this indicate you have complex conjugates?
Yeah.
Sure does. Because over here, if I click on this one, my gain is 512. And if I'm within the ballpark here, I was off a little bit, 439. Can't get there. I guess it's too close. So you can see 1.43 at 6.63. You can see they're almost the same. They're not exactly the same because, I can't get exactly 512. Yep. So this is other good thing too, which is your damping coefficient, zeta. That's shown over here. And then you also have your percent overshoot, and then you have your radian frequency. So this, I believe, is your natural frequency, and this is the damped frequency. Because if I look over here, look what happens to my damping. It becomes a positive number. I don't even know why they calculate damping in the right-hand half plane, because it just eventually just oscillates for forever, right? It gets bigger and bigger and bigger, so you don't technically have damping. Maybe that's why they call it a negative number, because negative damping would imply it doesn't actually make it smaller, it makes it bigger. Yes, sir.
So is there a gain on that curve right in the process of the vertical axis? Is that what our upper limit that we calculated from our?
Well, let's check. What did you calculate in lab? Does that answer your question?
I noticed it was larger than that going out to the left as well.
To the left?
It was
Great question. Let's pick a point over here. Come on. That gain is 2,000. So is that okay? Why not? Why is the gain too big? You can have a gain of 2,000.
It's outside of our range. It's the other side.
Yeah, because this one is a stable system, right? But don't forget, I might have 2,000 that ends up over here. See? This affects 3 separate poles. So no matter what I do to K, I'm always stable on this root loci over here. But over here, if I go to 2,000 and something, whatever that was, you can see that it's in the unstable region. So it affects 3 poles. That's the reason why you had to limit it at 120, because I'm okay over here with these roots as well as this one. This one's always okay, but these 2 are not okay. That's why you limit it at 120. So 120, what we determine is if you exceed 120, you're no longer a stable system. But it's only these 2 poles here that make the system unstable. Anything over here is not going to make the system unstable. So I can increase K to whatever value I want, and it's not going to make this pole unstable. But these 2 will be unstable. So I have an unstable system, because remember the rule of thumb, any pole in the right-hand half plane, any pole. I've got 2 poles that are in the right-hand half plane when K is greater than 120. So that makes the system unstable.
But then how would you have the K with the 120, but the only still stable? Do you have to remove those poles?
No, because with a K less than 120, these poles are also stable. They're in the left-hand half plane.
The K is the K within 120 this side.
K is greater than 120 here? Doesn't matter. This is in the left-hand half plane. It's always stable, right? So if I'm over here, it doesn't matter what my value of K is. This is always going to be a stable system.
Because I think you can understand that when you add it, K on top of the K above. If you put in K above 120, already it's unstable. But then I'm thinking, then how would you have a stable with K on the other side? I mean, it makes sense.
K, well, it's not K, so the poles would be on the right-hand half plane.
If you set your function, put in K above 120, then the graph is unstable.
Correct.
But then here on the side, K, the gain is above 120.
Right over here?
Yeah.
Doesn't matter. If remember the rule about a stable system or not, any pole in the right-hand half plane makes the system unstable. Any pole. So if I have one pole over here, it is regardless of what's happening over here, it's an unstable system because I have at least one pole in the right-hand half plane. All the poles have to be in the left-hand half plane for the system to be stable.
Okay. So where do you okay stable versus not stable? That just left half plane.
Left-hand half plane.
I didn't know if it was like outside that curve versus like a little bit inside that curve. Something like that.
Nope, just the left-hand half plane. It all goes back to our concepts of marginally stable, stable, or unstable system.
Does this graph change if you change that value?
Which value of one?
Okay, the the K, yeah, it's probably one for K. Yeah, when you, that.
Well, if you have a value of 1, k equals 1, then you don't do a root locus, you just have a single plot.
But when you plotted this, in the transfer, one substitute one.
You can't do a root locus because when you do MATLAB, when I do this transfer function, I can't have variables that are changing in here as well. So I can't have 2 variables. You can only have that
So
one.
change that value. Yeah, if you put 20, what, how would you do?
20 where?
So we put up one there for 20 and then one there for 20.
So I put what, 20?
Yeah. And then there also the last one too. 20. How would you?
You can't do a root locus because now the gain is fixed at 20. So at that point, I would do a PZ map.
Nothing. Yeah.
No, k is a variable, right? You can increase it.
Then why did you put the number? Yeah, you substitute 1 for K, it's not one.
Nope. No, this is just the base transfer function to go ahead. I'm still, so basically what I'm doing is I'm factoring k out. And then I'm keeping it as a gain. So what I'm doing is my open loop transfer function. I basically have. Come on. So the transfer function, whatever you gave me, was 1 over s cubed plus da 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 da. I just factored out my value of k and put it over there. So I didn't make it a 1. I factored out k over here, and now I multiply the transfer function by that value. So it's not 1. K is still variable, but I just multiply it. I moved it out. I multiply it later. That allows me to change k. Say that again?
Yeah, I would take it from the bottom. But it's actually, there's still. Exactly.
I'm not following your question. I'm sorry.
Multiply k, it's just gonna go to the top, nothing more than plus k at the bottom.
Yeah, but that's okay, because remember, as long as this value of k somehow gets put into there, then I'm good to go. It's just affecting its transfer function or expecting the characteristic equation. I really want to be able to put this value of k over here and allow that to shift, and that's what the root locus does.
So you put K on the last one and on the first one.
Yep. But really, all I care about is in the denominator, because that's the characteristic equation, right? That's what's going to give me the poles. I don't care what the number is up here. It doesn't affect poles and zeros. I really only care about it down here.
So you must always have one.
Well, if you want to be able to do it in MATLAB, right? I've got to put numbers in. Whoops, I've got to put numbers in here. I can't have variables. I can only have one value of k that is being varied. And that's how you set it up. You factor out your k's, and then you just do your base transfer function without that gain in there, and then you do a root locus plot. That's it. Questions?
So you don't have to mark anything on that one pole that goes up. You don't need to draw a line with it. You just want to call it stable inside of that, right?
Say it again.
When it asks in the lab, label where it's stable versus not stable.
Yeah.
We don't need to draw like a passive code at 120
No.
where the green is 120.
Nope. Anything for k being less than 120.
You just know that it's in the right and half.
And then it's an unstable system. Yep. That's all I care about. So this whole thing, if you wanted to append, you can say, let me see if I can annotate. That would be my stable. So if you wanted an additional clarification, because the thing about MATLAB is it doesn't show what the value of k is unless you click on those points. And then you can just go ahead and say anything for k less than 120. Here are my results. I've got a stable system. Okay. We'll be doing a lot more of this, I think, in the next section after we get through steady state errors, because there's a lot of calculations that need to be done. Because one of the nice things about MATLAB is MATLAB can do 10 million calculations in half of a second, right? How long would it take you to do 10 million calculations? A lot longer than half of a second. So what we need to do is we need to be able to draw these things without actually having to do a ton of calculations. We'll do some, but we won't have to do all of them. So we'll do asymptotes, angle of asymptotes, centroids, breakaway, break-in points, J omega axis crossings. We'll do all those. All right, any other questions on the lab? Yeah, like I said, I've been doing this a little bit through the semester, and even last semester, when I was introducing poles and zeros, and I said, hey, when we look forward, you have to have the same number of poles and zeros. And maybe I even think I said, because I have a mantra, if anybody knows what a mantra is, you say it over and over again, it kind of gets burned in your brain. So for doing root locus, I always say start at a pole, end at a zero, start at a pole, end at a zero. And if you say that enough, it starts to help you understand like how to lay these out. And so last semester, I think I did say it once, start at a pole, end at a zero. That's a precursor for what we'll be looking for this semester, but we won't go too crazy. Whoops. What happened? It's weird. All right, another advantage of living in the time domain. We can calculate things in the Laplace domain or get information from the Laplace domain exclusively by looking at Laplace domain results. And so one of the things that we're going to do is calculate what the error is going to be. And if you think about it, an error is just something you wanted to achieve a certain value, but it in fact is not that value that you want. So we're going to change some of our terminology. Instead of an input, we're going to change that to a set point. Because in the real world, if you do process control, our friends in process control don't want to hit it with a unit step input. They want to dial up a certain value to get a tank to go to a level. So that is our set point. Okay, and it just so happens that it's an input and it might be a unit step input, but we're trying to control that. And the fact that you have an error between your set point and what you actually have means you have to continue, or hopefully have the ability to continue to adjust your system so that you can force your error to zero. And so we'll see how we'll adjust things a little bit or modify things a little bit to go ahead and get our values that we want. So that's why we talk about a constant reference input. That's our set point. That's another way to say set point. Constant levels. It could be temperature. It could be flow rate. It could be level in a tank. Another way to say level in a tank is called head. So when they talk, and this is just an old mechanical engineering technology, the height of a water, and I don't know where the term head came from, is indicated by how many feet of head of water do you have, which water is dense. And so typically what happens if you have 10 feet of head, the bottom of the tank is going to have a much greater pressure than the top of the tank because the density of the water has more weight. And so that's how you can actually measure what the level of a tank is. You don't actually measure the level, you measure the pressure at the bottom of a tank. And so one of the things when I was in the nuclear world is if I had a device over here monitoring the pressure, I could tell you the level. So if I know what this pressure is, and I knew what the density of the material inside the tank would be, I can tell you the height of the material. Except, what if this is a pressurized tank? So if this is an unpressurized tank, if it just has normal atmospheric pressure, then what ends up happening is your pressure is pretty accurate. But there's a sneaky thing about pressure. So ambient pressure changes, right? Like today, it's rainy out there. The atmospheric pressure is probably a little low. If you're at the top of a mountain, the atmospheric pressure might be pretty low. So the pressure changes on a bunch of different factors. So to make this pressure measurement accurate, you need another port. And that just measures what atmospheric is. And so the difference between this input and this input is actually the water weight or whatever the process is. So if you have a tank that is pressurized, how would you make sure that you get an accurate result? Exactly. All I have to do is zero out what the pressure of the tank is. So maybe it's 50 PSI. So I feed that to this pressure. This is my reference. This is the reference side of things. And then now I can accurately indicate what that level needs to be. This can get more complicated though, because temperature here can really mess things up. So if your temperature of the whatever the process here can vary widely, you also have to feed that into your pressure so it can do some correction. But the thing you can't correct, or at least I've never seen it correct, is the material inside. So if the material inside is 80% clean water and then 20% some other stuff, but it could vary between 70 and 90, then your level can get all screwed up. So you can't adjust for the density of the material. I just have never seen that. Yes, sir.
Would you adjust density of like constant material to temperature though? Is that why you enter temperature?
Yep. Yeah, if the temperature inside the tank or whatever isn't going to change all that much, you might not necessarily need to do that. The ones that I've seen, they have temperature correction typically, is what I've seen. And so the only reason why I've done this, like I said, when I was at nuclear power plants, they had pressure transducers that would indicate what the level was. And then they had and it was amazing to see, they had the all 100% fail-safe approach. What's the number 100% fail-safe approach to detect the level in the tank? What's that? Don't want that because then the water's spilling out and it's a pressurized tank. So it would actually be something else. A sight glass. You can't have a window because if it's under pressure, the window's going to probably break. And so what you do is you pipe out a sight glass of really small value, a small amount, and then it actually has the ability to move up or down, whatever the material is in there, mercury or whatever, and it just adjusts that. And so one of the things that was amazing to me, we actually got to go inside the containment building and look at this sight glass, and the operators had to periodically, I think it was once every 2 hours, had to walk by and measure what the level was on the sight glass. So sight glass is based on basic physics principles, right? If you don't have a blockage, the level in the tank is what's indicated on the sight glass or the sight gauge. So that's always bulletproof. Maybe not the best, because you got to send somebody out there and they got to say, well, it's about at this line over here, and you're squinting at it. But, sometimes those tried and true things, right? They always work. And especially for you, where you're going to be going, it's always nice to be like, why is this pressure transmitter telling me tank is it cannot be 80% full? So what you do is you get your butt out to the field or the floor and go see if they have the ability to look at the tank level, either by looking inside, which is always a bad thing to do. You never want to look inside of a tank. Why? Could fall in. But the other thing is, what's inside the tank? It's probably not the best water if it's an industrial facility. So if you're looking over and breathing in whatever's there, then, that can cause you some health hazards. And then the other thing, which is another more subtle thing. So if you walk up there and we're all engineers, we're all nerds, and we have our pencil protectors, right? And we lean over and falls in. Now you've just contaminated that water. That's the quickest way to get kicked out of a job, is to make a mistake like that. So it's better to just have a sight glass because it's a enclosed process. You can look at the level. You don't have any issues. Just lesson learned from somebody who's seen a few things in the field, and it always just surprises me or scares me. I have been teaching a long time, but in the 10 or plus years that I worked in industry, I did get to see a lot of really cool, sometimes crazy things. So hopefully, the world is a lot smarter than when I was learning how to be an engineer, because stuff I got exposed to was not always the safest. I almost lost a finger one time helping people out, and I had to crawl through some fish stinking water because just to check to see if there was some debris on the other side of this pump. And even though I had no idea they'd turn the pump, it was a valve. So I had to kind of dip Superman through the valve and then go check out the screen to see if there was crap in there. So I didn't know the valve could have opened or closed, and I would have been stuck in this valve. I would have died. I mean, but you just somebody told you to do it, so you did it. Kind of crazy stuff. So anyway, so temperature control is a set point, right? Cruise control is a set point. You do have some feedback in both cases. What's the speed of the vehicle? And then what is the temperature in the room? How about more difficult ones like tracking? So what I mean by that is you're tracking an object moving. So if a vehicle, you're trying to track it with maybe some sort of military system, you're trying to track it, and you know what the speed is, it has to increase its position with a ramp characteristic, right? So it's going this way. Or what if it's accelerating and you're trying to pick up something that's moving at an accelerating speed? That would be the example. So when we do control systems, we want to have it to all broad categories. Most of us, our set point is going to be one of those. It's a unit step. It's not necessarily going to be a ramp thing unless you're trying to ramp up something at a certain speed and maintain that level. Okay, so here is a stable. So that's the first thing. You can only have steady state error calculation if you have a stable system. All right, remember that. If you look at a system and you have a pole in the right-hand half plane, then your steady state error is infinity. There's no work that needs to be done because eventually, if I provide that with a bounded input, the output's unbounded, so how can I ever have a stable system? I mean, an error that goes to a smaller value. So this is showing it as unity feedback, but it doesn't need to be unity feedback. We can have a system here. And now we're going to divide our system into two parts, a controller and a plant. The plant is fixed. That's whatever was constructed to do whatever process or whatever thing that you need to do. So my plant is stable, it's fixed, it's not moving. The controller is something that you, the designer, add in to provide control. Another way to say that, for maybe those of you who have taken PLCs with Jude, how about a PID controller? Everybody know what P stands for in PID? No. Partial? No. 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 Let's do it this way. Probably. It's a proportional controller. So if you have a proportional only controller, you hit it with an input, whatever that input is, and then it outputs a signal that is proportional to the input. So this is essentially multiplying it by a constant K. The I, as everybody said, is integral. And this is derivative. This here, right, we have the integral, and this here we have the derivative signal. Now, if you go with a proportional only controller, that may work, but there's a problem with it. You always have to have error. Why is that? Remember this here, because this is my set point for what I want. This is what I have. What's another way to say the difference between what I want and what I have? Error. This is the error. I know that sounds harsh, but I don't have what I want. So I have error between my set point and the actual output. And so a proportional controller only works because if this error equals 0, the output of the controller is 0. Right? Which means there's no input to the plant. So I have to accept error for this not to be equal to 0. So if you're okay with setting a set point and not actually achieving your set point, then a proportional controller input is perfectly fine. If you want to get rid of the error, you put an integral. Why is that? Why would you put an integral in there? I add it to my controller. Here's my error, right? Say it's constant. My proportional is always going to output something like that, right? What does my integral do? It integrates up, doesn't it? As my error stays, I keep integrating and integrating and integrating and integrating until hopefully my error goes to 0. So by adding the integral controller, you actually have a system that will give you no error. In most cases, if a step input is what you want for a set point, then you're feeling pretty good. The derivative control, what does the derivative do? All the derivative does is when that error comes in, it gives you a little bump. And if the error is constant, its output is 0. So when would you use a derivative? Pardon? Well, I can do that with proportional and integral, and I can see with proportional and integral control, I can force the error to 0. When do I add a derivative control part of it? This is a tough one. Well, you don't know if the error is going to change, right? That's the thing with a controller. It has to be able to go for all cases and conditions. Derivative is usually there to slow a system down. Think about a thermal process where you're trying to control the temperature of something. The difficulty of a thermal process is the temperature is too low, so you're putting more heat into a system. The temperature doesn't instantaneously change in that process, right? It takes time for the temperature of whatever you're trying to heat up heats up, but then also you have a device that's measuring temperature, and that has a time constant as well to heat up. So you're blasting this thing with lots and lots of heat, and then your system finally catches up, and now you get your set point, whatever your set point is. But because you've been blasting it with heat for a long period of time, you actually will overshoot your temperature, and then you have to kind of go back down. So what you have is you have oscillatory response. You're always hunting, trying to get that value. So by adding derivative control, you actually will try to slow your system down. So you would subtract the derivative error, and then you hope that your proportional and integral are going to go in and so that you can get the value that you want. So normally when you say PID, it's P plus I minus D. And the D term is only used on a sparing application. Most of the time, all you ever need is proportional plus integral control. You very seldomly use derivative control. It's there, it's available to you, but it works pretty well. Okay, I mean, it doesn't always work really well. All right, so here's our ESS. Oh, not our ESS. So here's our output multiplied by the transfer function of our input. And this is G over 1 plus GH. Notice that H is equal to 1 over here. So that's why you have the same numerator and almost the same denominator. My steady state error is calculated over here. Sorry for the mess. I just put a lot of material on here. So my error signal, the difference is going to be calculated between what I want and what I have, R minus C. And so then I just move that in and factor it out. Anybody see how I got this value here? I got 1 plus GC GP. It doesn't look anything like here, does it? Does everybody see how I got that? Or you want me to show you the algebra? All right, so let me go ahead and copy over. Come on, move up. Oops. Okay, so we said our C is equal to G controller. G plant over 1 plus G controller, G plant times my value of R. And then I said my error is equal to what I want minus what I have. So that's equal to R minus GC, GP over 1 plus GC, GP times R, correct? Now what I'd like to do is I would like to do some common denominator stuff, right? So that's equal to R times 1 plus GC, GP minus R times GC, GP all over 1 plus GC, GP. Anything tricky that I've done there other than just common denominator? Now I can see this is R times GC, GP. This is minus R times GC, GP. So those two go away. And what I'm left with is R times 1 over 1 plus GC, GP. Which is if I go back to here, that's what I calculate. Any questions on that now? See how I got that? So now I'm going to do my steady state error signal. I'm going to calculate my steady state error, which is going to use my final value theorem. Whoops. So ESS, I take the limit as t approaches infinity. E of t, that's the actual time domain value. But now I'm going to use my final value theorem, which says let the limit as s approach 0, s times E of s. That's going to be equal to the limit as s approaches 0, s times R over 1 plus GC, GP. And now I'm going to describe a brand new term. And this brand new term is called my open loop transfer function, which essentially, guess I'll do it over here because that's pretty messy. And I talked about this already before. Why is this really? My computer just doesn't want to work today. GC, GP. I'll put a feedback block in here, but we can make this H equals 1. And the whole thing about an open loop transfer function is I open that closed loop. And my open loop transfer function is the transfer function between this point and this point. And you can see how that signal comes back through here. So the open loop transfer function is GC, GP times H. It doesn't go back and go any further, right? It just goes back to that point. So I don't actually do any 1G over 1 plus GH. It's literally just, I'm treating it almost like it's a feed forward path. So if you wanted to kind of stretch things out and rotate them, you end up with a path as shown in that direction. Okay. So here's my open loop transfer function. And if I factor out my open loop transfer function, you will note I have an S to the N over here. S to the N is really important to us. What does an S in front of my entire denominator equate to? A what? An integrator? What else does it integrate to? Not a step input. The pole at S equals 0, right? Same thing? You have a question? What do you mean? It's an unstable system, or I should say marginally stable system. It just depends on the input, right? So if I hit it with a unit step, then I could have some problems. But if I don't hit it with a unit step, then it's perfectly fine. So this S at that pole at S equals 0 tells us something. It is called the system type. And the system type, the system type is a number, type 1, type 2, type 3, type whatever. And the system type is equal to n. So n is the number of poles at s equals 0, or it's the number of integrators. Because if my system itself has 50 integrators built into it, right? Because my controller has, maybe it's a really sophisticated controller and has a lot of integrators, then it's going to be able to integrate out a lot of different input signals without having to give me any problems. Let's see the time here. We'll go for a few more minutes since we've got a light class, and I'll let you out a little early since it's the day before break. Unless you want to go full Monty time, it's up to you. I know some people in 321 probably want the extra time to do the homework. Although nobody came by my office this morning except for non-EET students. I had somebody at my door at 7 and somebody at 7:30, and they were non-EETs. I was surprised. So
I'm just wondering. Yeah, I mean, it's fine.
you didn't want to get up early?
We stay to play the cup after the class.
Ah, you want to get up early, but yeah, they were able to get that done. So
Yeah, there's a build in.
oh, okay. All right, so here's my steady state error. So I'll do an input, a unit step input, A of S. So I'll do my limit function. And you can see this is the S from the demand. My input is A of S, right? Because a unit step is A over S. Now I'm going to just move I'm going to cross out my S terms. And I can move my limit function anywhere I want. And I'm going to move it here into the denominator. Why am I moving it into the denominator? Because that's the only one that has S in it. If I take the limit as S approaches 0 to this, why does A care? A doesn't have S in it, it's a constant. So there's no work that needs to be done for A for a limit function because it's not dependent of S. And what I end up with is that a simplified expression that has this term K sub P in it. K sub P is defined as our position error. And you'll see where our position comes up in a little bit. It's the error of just, what would the position be? And if it's a type 0 system, no integrators in the system, then my steady state error becomes this, A over 1 plus K sub P. Okay? What happens if I make it a type 1 system? I add a single integrator in there. My controller is a P plus I controller, so I have an integrator built into my system. So what happens? Well, remember, this is going to have an S term out front here, right? So, whoops, it's 1 over S, sorry. I know I'm going to have an S in the denominator because that's what the characteristic equation is. And when I take the limit function of that as S approaches 0, doesn't the 0 here in the denominator mean that this whole expression goes to infinity? Let me pull that out so you can see. And I have my S term that I've had for the integrator. Doesn't this equal infinity? You plug in S equals 0, something over 0 is going to be equal to infinity. So my K sub P term becomes infinity. When I stuff that into here, A plus 1 over infinity is equal to A over infinity, which means my steady state error goes to 0. So if I hit a system with a unit step input, I darn well better have at least one integrator in my system, or else I'm going to have to tolerate some amount of error in my system. If I have one integrator, then I will have no error in my system. How about 2 integrators? Goes back to type A. Well, 2 integrators means this, S squared, which means this. Does K sub P change? Still infinity. So my ESS goes to 0. And on and on and on and on and on. So if I go 0, got an error, 1, no error. Anything beyond 1, I have no error. 1 and beyond, no error. 0, I have error. That's what that summarizes there below. Okay?
So when you say type 0, does it mean that, n is equal to 0?
Yes. Because n is the number of s's or number of poles at s equals 0. So if I have an s to the 0, what does s to the 0 equal to? 1. So over here, that's equal to 1, isn't it? So I don't have any problems with that. Doesn't blow to infinity. Okay. Let's do one more and then I'll let you go so you can have a nice day. Get started on break early. Let's do a ramp input. Now we're tracking a system, right? We're tracking something moving. So we've got to move it along at a ramp. So my input is A, some constant, doesn't matter what it is, times T. So the input now has a T in it. So that's how you get a ramp up. When I convert that into the Laplace domain, I know that I have an AS squared. So now let's look at my error signal. So remember, that's 1 over 1 plus GCGP, and I still have to multiply it by R. So that's why I have my A over S squared. I can see that one S term gets canceled out because of that system. So now I'm going to distribute my S term into that function. So I have the limit as S approaches 0, I have an S term. Then I have an S times GC of S. Well, I know that this term, the limit, I can bring that out separately. So limit as S approaches 0, S. We know that that's always going to go to 0. So I can throw that term in the trash. The other term I have is over here. Okay? So we're going to define a new term called the limit as S GCGP, or limit as S approaches 0, S times GCGP. We're going to denote that as KV. And remember how we said over here, K sub P is the position error? What if I multiply this term by S? If I multiply the position error constant by S, what do I have? First derivative of position is velocity, right? Derivative of X is velocity. So that's where the proportional and the V comes from, because P, there's no derivative. V is the first derivative of GCGP, and you get that value. So if it's a type 0 system, then I can see that my K sub V term is going to be equal to 0, right? Is that a good thing? K sub V being equal to 0? Sounds like a good thing, except the error is A divided by K sub V. A number divided by 0 is infinity, right? As steady state error is infinity. What I want and what I got are going to continue to separate for a type 0 system. How about a type 1 system? Now the S's will cancel, and now I'm just going to end up with A over K sub V. So I'm not going to get 0 or infinity for an error. I'm going to get some error. Then if I move to a type 2 system, then I can see that the S squared term cancels with the S term. That approaches infinity. And my steady state error term goes to 0. So if you're trying to track a ramping input, you darn well better have 2 integrators in there to make sure that your system error goes to 0. If you have 1 integrator in there, you're always going to be behind. You're always going to be chasing whatever you're trying to get to, but you'll never get there. If you have a type 0 system, just wave goodbye, because you're going to fall further and further. Questions on that? people are baiting, as are you, so. All right, I'll call it. Have a great break. And I will see you after break. Take care, everyone.
It was fun.